Another example is the one shown here. What we want to do is to model an adder that takes two 4-bit inputs and produces an output which is 5 bits. We want this to be a signed adder, so we treat our inputs as signed quantities, 4-bit signed quantities, and we obtain a 5-bit signed output. We label the inputs A and B, and the output is labeled sum. A common requirement when building arithmetic circuits is that we often have a carry-in which we have an extra bit that we need to include in our adder. And this is a 1-bit value. The carry-in value can be either 0 or 1. And because it's a 1-bit value, in order to represent a 0 or 1, our carry-in bit must be unsigned. If we were to make our carry-in bit signed, the only values that we could represent with a signed 1-bit number are the values 0 and -1. This is not what we want, so we have to stick with the carry-in being unsigned. So we still want to perform a signed addition to produce a signed output. Let's illustrate the operation of this signed adder with an example. So let's say A has the value -8, B the value +6, and Cn can only be 0 or 1, so let's say it's 1. So when we add these three values, we have -8 +6 +1, which is equal to -1. And that's what we'd expect to get at. In binary, the 4-bit value for A is 1, 0, 0, 0. It's a 4-bit signed value. For B, it's 0, 1, 1, 0. And for the carry-in, we have the value 1. And our 5-bit output representing -1 is the following 5 bits. Our module, which we call signed adder with carry-in, models our adder. We have the inputs A and B, signed 4-bit values. We have the input Cn, an unsigned input. And then we have the output sum, a 5-bit signed value. And we perform our addition in this way, adding A, B, and Cn. The expression tree for our expression and assignment looks like this. We have two context-determined operators, both addition operators, and the result of the second addition is then assigned to sum. A is signed, B is signed, Cn is unsigned, and sum is signed. Starting with this context-determined operator, we can quickly see that the addition will be a 5-bit addition, yielding a 5-bit output. The next question is whether the output is signed or unsigned. Well, both our operands to the addition are signed, but remember, because it's context determined, we have to look to other parts of the expression, and we see that Cn is unsigned. And because all three are not signed, this is a 5-bit unsigned addition. So the output is an unsigned output. And because it's an unsigned addition, producing a 5-bit output, the 4 bits need to be extended from 4 to 5 bits, and this will be using an unsigned extension for both, producing two 5-bit values for the addition. And our output is unsigned because it's an unsigned addition. We now look to our second operator, again a context-determined add operator. This is also a 5-bit addition, producing a 5-bit output. To determine the sign of this addition, the context is limited to the two operands. Both are unsigned, so we again have an unsigned addition here. Our Cn input is 1 bit that needs to be extended to 5 bits, and an unsigned extension is used to go from 1 bit to 5 bits. Using the values we had on the previous slide for A, B, and Cn, we have our two 4-bit inputs are extended to 5 bits. We use an unsigned extension for both, so we insert a 0 into the extra bit position, yielding these two values. Our value 1 for Cn is extended to 5 bits using an unsigned extension, giving us this 5-bit value. Performing this addition yields this 5-bit value. Taking our next addition, we have this 5-bit value here, which is then assigned to sum. This is a signed quantity, however, in decimal, it's equivalent to 15. And if you remember, our addition gave us the value -1. So the correct answer is -1, but the answer we get is 15. Our expression, which looks straightforward, is not correct. The key source for our problem relates to our unsigned extensions and our unsigned additions. And we need to address this in order to model our signed adder correctly. Let's have another go at modeling our signed adder. This time we make a small change. We change Cn to signed. So let's see what happens in that case using the same values. So now Cn is signed. We start with this add operator. We see that the output will be a 5-bit output. So we have a 5-bit addition. It's context determined. So when we determine the sign for this addition, we have to look at A, B, and Cn. And all are signed, making this a signed addition. And the output is a signed value. Because it's a signed addition, the extensions will be signed extensions from 4 to 5 bits. When we look at our second addition, we again see we have a 5-bit output. So it's a 5-bit addition. And when we determine whether this is a signed or unsigned addition, we need to check the two operands. Both are signed, making this a signed addition. So our output is a 5-bit signed value. Cn is 1 bit. We need to extend it from 1 to 5. Because it's a signed addition, we do a signed extension to extend our 1 bit to a 5-bit value. Let's now look at our values. This is -8 decimal, 6 decimal. And we have to be careful when we look at this value. The bit has the value 1, but because it's signed, this actually represents the value -1 decimal. So let's work through our operations. Our 4-bit value is extended to 5 bits. We take the most significant bit and replicate it. Hence we have a 1 in this bit position. For this 4-bit value, we take the most significant bit, which is a 0, and replicate it, yielding this 5-bit value. Here we have a 1, that is the most significant bit, and replicate it 4 times, and that gives us our 5-bit value. Performing this addition yields this value, and the second addition produces this value here, which we now assign to sum. However, in decimal, this is equivalent to -2, which again is incorrect. So the problem with this approach is that even though we ensured that our adders are all signed adders, we end up incorrectly treating Cn as a signed quantity, which is not what we want to do. There is a way in which we can address this problem. Let's go back to having Cn unsigned. Cn is a 1-bit unsigned input. The main problem with Cn is that we want to represent values 1 and 0. And we saw in the last case that if it was signed, we represented values -1 and 0, which we don't want. So one way in which we can achieve this goal is to create a 2-bit quantity with the second bit always 0. So we use bus concatenation to group this 1-bit value and this 1-bit value to form a 2-bit value. And with this, we can have the two values 0, 1 and 0, 0. So the goal of doing this is that if we do end up doing sign extension, a 0 is in the most significant bit position and thereby represents a positive quantity. We're almost there with solving our problem. We just need one further step. The problem with bus concatenation is that the result is always unsigned. So the 2-bit value is an unsigned value. In the 2001 update for the Verilog language, 2 functions were added. The 2 functions are the signed function, which takes 1 argument, so you can supply any expression to that function, and the function unsigned. Again, has one argument in which you can supply an expression. Note that built-in functions always start with a $sign, and these are known as system functions. The signed function is of interest to us here, and what it does is it returns the bit value of its argument as a signed quantity. Equally, the unsigned system function returns the bit value of its argument as an unsigned quantity. If we supplied this expression as an argument to the signed system task, it will return the 2-bit value as a signed value. So what we now get is a signed 2-bit value with either this value or this value depending on Cn. So let's look at what's happening. Our concatenation operator is combining, in this case, two expressions, the 1-bit value with the value 0 and the 1-bit value Cn. Both are unsigned, and when we combine them, we're combining 0 with 1 to give us a 2-bit value which is unsigned. So we have a 2-bit unsigned value resulting from the concatenation. We didn't supply that to the signed function. You can think of all functions as self-determined, and our signed function takes the 2-bit value 0, 1 and returns the same 2-bit value but as a signed quantity. In our previous examples we had the following: assign sum equals a plus b plus cn. So what we want to do now is replace Cn with this new expression, and this is what we have now. We can now complete our expression tree. The only difference is that Cn is replaced with this part. So let's work through our expression. Taking our first addition, it's context determined. It depends on a, b, sum, and the output of the signed function. We've got the following sizes: 4, 4, 5, and 2. 5 is the largest, so the output of our addition is a 5-bit value. So we have a 5-bit addition. To determine the sign, because it's context determined, we look at the sign of A, the sign of B, and this sign. All are signed, so that makes this a 5-bit signed addition, and the output will be a signed value. The inputs to this addition need to be sign extended, since it's a signed addition from 4 to 5 bits. Let's now look at the second addition. We've now got 5, 2, and 5. The largest of those three is 5. The output is a 5-bit value, so we have a 5-bit addition. Looking at the signs, we've got a signed input here and a signed input here. And remember, we don't consider what's to the left of the assignment, so we don't consider this. But because both of these are signed, we have a signed addition, and the output is a signed value. We need to extend our 2-bit value to a 5-bit value. Because it's a signed addition, it's a signed extension. Next, we'll complete the evaluation of this expression for our sample values. A has the value 1, 0, 0, 0. B the value 0, 1, 1, 0. Sign extending these two quantities yields these two values. Adding them produces this value. We have to sign extend our 2-bit to a 5-bit, and when we do this, the resulting value is 0, 0, 0, 0, 1. We're now left with one more addition, producing 1, 1, 1, 1, 1, which is then assigned to sum. And in decimal, this is equivalent to -1 decimal. It's a signed quantity, and this is the correct answer.